Chapter 2, Section 2.2, Polynomial Functions of a Higher Degree. Here are our section objectives. And we'll start with graphs of polynomial functions. So in the previous section, we only looked at quadratic functions, which should have a power of 2. Here we're going to look at higher order functions, so it might have a power of 3, 4, 5, 6, a bigger power. The first feature of polynomials is that they're continuous. You won't see a jump or a hole in these. They're going to be a smooth continuous curve that passes the vertical line test. So it's a function, it's continuous, it's just going to be curvy. Here's another example. It can have turning points, but it will just be smooth. There won't be corners or cusps, jumps, or holes. So often you'll see me refer to this first exponent or the biggest exponent as the power of it. And so if it has a power of, 3, 4, 5, that would be the power of the function. So when you're looking at these, you want to have an idea of what the parent function looks like and then how the transformations can be applied. And so this first one, if we have, f of x equals negative x to the 5, the x to the 5 would be the parent function of it, and then the negative would flip it. So if I'm looking at just x to the 5, the first thing I'm going to think about is, it's an odd power. An odd power means it will be very similar to other odd functions like x cubed. So if x cubed is an s curve, x to the 5th is also an x curve, or an s curve. It's going to look very similar to x cubed. Now with the negative, we learned earlier in the textbook that a negative will flip it over the x-axis. So instead of seeing this s curve, we're going to see this curve. It has been reflected over the x-axis, and it looks like an x cubed function. Now this one, the parent function would be just x to the 4th, and it's even, so that is going to look very similar to x squared. So x squared is going to be a parabola, x to the 4th is just going to be a slightly flatter parabola. So we can kind of visualize the parabola, but we know it's slightly different. And then here, the transformation is inside the parentheses, +1. That means it will move left 1. So here is our solution. You can see it's a kind of flatter parabola moved to the left 1. The leading coefficient test is a way for us to ensure that we have kind of the basics of our graph correct. It's going to tell us if the ends are pointing up or they're pointing down. So we'll take a look. If your n is odd, if it is like, for example, y equals x, or y equals x cubed, or y equals x to the 5th, if that power is odd, we are going to have something like an S curve. Y equals x would be a flat line. Cubed is an S curve. 5th is similar to an S curve. But what we're going to always see there is on the left side, it points down, falls. We call that falls to the left. And then on the right side of the graph, we will have that rises. We'll say rises to the right. So if you have an odd function, you will always see that if a is positive. Now, if you have a reflection, if a happens to be negative, that means the whole thing is flipped. You're going to see the opposite. You're going to see rises to the left because now it's been reflected, and then you'll see falls to the right. That would be like y equals negative x, y equals negative x cubed, y equals negative x to the 5th. You might see a different a value like 2, 3, 4, but it's negative if we are looking, at the second case over here. Now, if n is even, that would be like x squared, x to the 4th, x to the 6th, something like that. If your a is positive, you're going to have some kind of parabola looking shape. you know, something like this. It might have these extra fun, you know, turns and vertices and stuff like that. But in the end, you are going to see the basic parabola shape, which means you're rising on the left and rising on the right. So we'd say rises on the left, and we'd say rises on the right. Now, similarly to before, you know, if you have a negative exponent here, that means you're talking negative x squared, negative x to the fourth, negative x to the sixth, something like that. Now everything has been flipped over the x-axis, so you are going to see falls. So you'll see falls to the left, and you'll see falls to the right. And those are the only 4 cases. We've hit them all. You know, rising and falling, left or right, even odd functions, positive a values, negative a values. All right, so here we'll do an example. It says, you know, it actually has lots of terms in these. So what we do is we look at the term with the largest power, and we focus on that. Negative x cubed is what we'll focus on. This extra term doesn't affect the graph enough to change the leading coefficient test. So we only look at this. Odd is our exponent, so that means we'll have the arrows going in different directions, fall and rise, because it's odd. And then negative means we are going to see not a regular, you know, not a regular S-curve, but we're going to see the flipped version. So we would say this would be rises to the left, because on the left side of the graph it's going up, and then we'd say falls to the right. That would be our behavior, our arrow behavior for part A. All right, part B. Part B. Now I'm looking at x to the fourth. I look at my term with the biggest power. X to the fourth, we're talking even, so my arrows will both be up or both be down, and it's a positive a. So that means it's an even function, looks like a parabola. It's up because a is positive, so we're going to say rises to the left. Oops, rises to the left and right. All right, last one is C, so we have x to the fifth. That's our largest power. We're talking S curve because it's odd, and it stays like that because it's positive a value. It's not been flipped. So here I'd say falls to the left. Here I'd say rises to the right. That's for part C. Here is a graph of the exact function, so you can see that we were right with our, you know, my really rough sketch. Here is what we're looking at with an exact graph, and the behavior falling and rising on the left and right. There's part B. There's part C. All right, real zeros is next. Zeros is what makes the equation equal 0. So if you're looking for a 0, you're looking for an x-intercept, you would set it equal to 0 and you would solve. It is a solution to the polynomial. If you set the function equal to 0, the 0 is a solution. We will be looking at different types of functions and you know, talking about algebraically how to do this. So find all the real zeros. What I have to do if it asks for zeros is I have to write the function and set it equal to 0 and solve. Often factoring is going to be our best bet depending on the polynomial and if it's factorable. So here I'm going to factor out the greatest common factor. I'm going to take out a negative 2x squared. That leaves me with x squared minus 1. X squared minus 1 is also factorable. So I'll factor that into x plus 1, x minus 1, and now I have 3 factors. 1, 2, 3. When you're solving by factoring, you set each equal to 0 and solve. So if I set this equal to 0, I divide by negative 2, I would square root. I get x equals 0. Here I'd set that equal I'll show you. I'll set that equal to 0 and solve. I have x equals -1. Here I set the third one equal to 0, and I get x equals 1. So finding the real zeros, I got 0, 0, -1, 0, and 1, 0. Oops. 1, 0. It also says determine the maximum number of possible turning points. Well, that is easy. It's just 1 less than the power. So this is 3 possible turning points because the power is 4. So there is the typed out version of factoring. And then my graph, here are the zeros we got. And then there's the graph. It shows you those 3 zeros, and they're right at the x-intercepts. Turning points on a graph is where you go from increasing to decreasing. So like increasing is here, up, decreasing is down. So my turning point is right at that maximum. Here's another turning point and a third turning point. All right, if you have repeated zeros, like they pop up more than once, like your power has a factor, or your factor has a power of, 2 or 3 or something higher, we call that a multiplicity. And if the power is odd, the graph touches at that 0. If it's even, or crosses at that 0. If it's even, it touches at that 0. We will go ahead and take a look at an example. So I want to just look at a example of a polynomial, and we'll go through and kind of apply these things we've been looking at. So first, the leading coefficient test. That's going to say if the arrows on the ends are rising or falling. So we'll look here at that first term, and we'll see that 4 is even and 3 is positive. So we're talking even is up, up, rising, rising, and A being positive keeps it up, up. So we're going to say rises to the left and right. Because it's even, we're going to have some kind of parabola-ish shape, and it stays pointing up because 3 is positive. The real zeros is we're, setting it equal to 0 and solving. I'm going to try to factor this and see what happens. I'm going to factor out x cubed. So I get 3x minus 4. Looks like x is going to be 0 and 4/3. And when we're looking at this, we are going to see that the multiplicity of 0 is 3. So z has a multiplicity of 3. 3 is odd. That means it will cross at 0, 0. Because 4/3 has an invisible power of 1, that is a multiplicity of 1. We usually don't even say that because it's just 1. It's odd. That means it will also cross at the 0 of 4/3. Now, when here it is typed out. Here's our rising arrows, here and here, and then there's our zeros. In order to connect all these dots and have it look accurate, plotting additional points is a good idea. When I like to plot additional points, I like to pick ones that are in key areas, like to the left and right of each 0. So here is some intervals that I set up. -infinity to 0, that would be to the left of this 0, like over here. Let's get, another point over there. Let's get a point right here in the middle of those zeros to see what's happening. And then let's get a point over here to see, can we get some more accuracy there? So picking a 0 between -infinity and 0, you can pick whatever you want. I'd probably pick -1. You pick a number between 0 and 4/3. I'd probably pick 1 because it's easy. Pick a number between 0 and infinity. 4/3 and infinity, I'd probably pick, 2. Then you go and you plug those into the original value. If you plug in -1, f of -1 is 7. F of 1 is 1. And I haven't done 2 yet, so let's go back and plug that in. We can Go back, and the original function is 3x to the fourth minus 4x cubed. So 3, 2 to the fourth minus 4, 2 cubed. 2 to the fourth is 16, so 3 times 16 is 48. 2 to the third is 8. 8 times 4 is 32, so that would be 16. So what that does is it gives you, I forgot a negative here. F of 1 is negative 1. What that does is it gives you additional points. So like negative 1, 7 is a point on the graph. 1, negative 1 is a point on the graph. 2, 16 is a point on the graph. And then when you go in and you're graphing it and you're filling in the details, it gives you a more accurate graph. So when we graph it, we had 0, 0. We had 4/3 0. Then we had negative 1, 7. We had negative 1, or we had 1, negative 1. And we had 2, 16. Oh boy, 2, 16. It's really not going to be super to scale, but we're sketching it. So now both our arrows have to go up at the end, and we have to hit all these points. And we said at each x-intercept we're crossing, not touching. So we'll start with an up arrow, hit that first dot, hit this first one, and then I have to, turn and, let's see, I gotta hit that. I've gotta turn around, go up and up. So, it's a parabola looking shape because it's even. It has some turning points, and this is, my best sketch using the information that I have.